Okay, I'm going to go over how to do some calculations using the integrated rate laws, and I'm going to do it using, I'm going to model it using a simple reaction that is a first order reaction. Let's say we have chemical A going to product, and the rate law is R equals K, A to the 1 power. We don't normally put the 1 there. It would just be R equals K, A, concentration of A. But that's telling us that this particular reaction happens to be a first order reaction. The integrated rate law for that, which I showed you guys last time, is the natural log of A at a particular point in time is equal to minus KT, where T is time, K is a rate constant, plus the natural log of the original concentration. And if I were to take the concentration of A and measure the concentration of A in my reaction container over time, like I were to measure the concentration every 5 minutes or something, and then I were to take the natural log of that concentration and plot it versus time, I would get more or less a straight line going down. Notice these are my actual data points. They're scattered a little bit because they have some error in them, experimental error. I didn't measure perfectly. This black line going through the middle of them is my best fit line. The slope from the best fit line is equal to minus K. And this intercept right here is equal to the natural log of the original concentration. Okay? I'll go over this graph type stuff later, but what I'm going to do is I'm going to show you if we want to do calculations for this reaction, wanting to know the concentration later at a certain point in time. I don't want to use this particular form of the equation. Trust me, you want to use one of these two forms. If I were to manipulate this, I could get either this or I could get either that. You have to know how to use your logarithms, but I would use one of these two forms for the calculations. This form I wouldn't use for the calculations. I would use it for getting the rate constant and the initial concentration from measuring the concentration of this as it disappears over time. But if I want to do other calculations, I want to use one of these two forms. Okay? Now, knowing which one to use, if I have a problem that says the original concentration is this, what will the concentration be after X number of minutes? I would want to use this form of the equation right here. Okay? If the question asks, how long will it take for 50% of the chemical A to be consumed, then I would want to use this form right here, where this is a ratio and 50% is a ratio. Or if it says, how long will it take for 1/3 of the reactant A to be used? 1/3 is a ratio, it's a fraction. I would want to use this form right here. Okay? What I'm going to do now is I'm going to erase this, and I'm going to do a sample problem of each one of these for you guys to get the idea how this works. I cannot do every possible variation of these problems. It just would be way too time consuming. And that's, of course, what the purpose of homework is, to learn the basic principle here and then apply it in all the possible variations so you internalize it and master it yourself. So let me erase this. Okay? And let's say I have this reaction. A goes to product. And the question is, if the original concentration of A is 2 molarity, how long, excuse me, not how long, but what will the concentration of A be after, let's say, 75 minutes? Now, they gave me this and gave me this, but I need to know the rate constant. So the problem has to tell me the rate constant. And so I would have K equals, let's say, 0.25 minutes to the minus 1. That's K, the rate constant. So what I would do then is I go, the original concentration is this. What will the concentration be after a certain amount of time? That's not a ratio type problem. It's not a 50% or 1/3 or 1/4 or something. That sounds like this form of the problem. So then what I would do is I would go, the concentration at 75 minutes will be equal to, what's the original concentration? 2 molarity, E to the minus, and what's K? 0.25 minutes to the minus 1. And the time was 75 minutes. You'll notice the minutes cancel out. Then if I multiply these, here, 75 times 0.25, I'm going to get, 75 times 0.25, I'm going to get 2.00 molarity, E to the minus 18.75, and that's 2 sig figs there, so I'd probably go 2 sig figs, 17.75, right? That's 3 sig figs, so I'm going to 2 sig figs, 3 sig figs, I'm going to go to 2. E minus 18. 18.75, excuse me. It was originally 18.75, and then I go to 2 sig figs. That'll be minus 19. And so we're going to go 19 negative second function e to the x times 2 molarity. And I'm going to get 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 0, 1, 1. Molarity, which would be 6, 7, 8, which would be 1.1 times 10 to the minus 8 molarity. Okay? I could say, what if I worded the problem after 75 minutes, the concentration was 1.10 times 10 to the minus 8 molarity. What was the original concentration? And then they gave me K. Well, that means in this problem, I gave you this, I gave you K, and I gave you T. I could reword it where I give you this, I give you K, and I give you T, and you solve for A naught. Or I could give you this, give you time, and you calculate K, the rate constant. Okay, you could do that too, right? So I'll come back to that. Let's do one of these, all right? So erase this. Let's try here. If it takes 100 minutes for this first order reaction, right? It takes 100 minutes for the concentration to drop to 1/3 the original concentration, what is K, the rate constant? Well, this is a ratio or a fraction type problem. And if I said, instead of 1/3, I said 33.3%, that's still, you know, a ratio or a fraction, right? Because percent means per 100. This one, I know I'm going to be using this form of the equation, not that form. And what do they want me to solve for? They want me to solve for K, the rate constant. They gave me T. What do I do with this? Because they don't give me any concentrations in there. Okay, so what do I do? Well, it says here, for the constant, if it takes 100 minutes for the concentration to drop to 1/3 of the original, that means the concentration at that 100 minutes is equal to 1/3 the original concentration, right? Know what that means? So I could write the natural log A naught, that's original, and at the time we're talking about, this is equal to this. So I'll put that in there. 1/3 A naught. That's equal to minus KT. It said if it takes 100 minutes for the concentration to drop to 1/3 of the original, the concentration is equal to 1/3 the original. If I put that in, you guys see that that cancels out nicely. And then it says, what is the value of K? Well, I'm just going to solve now for K. I'm going to have T is equal to, excuse me, not T, I'm solving for K. K is equal to the natural log of 1/3 over minus T, right? I can put the minus in the front. The natural log of 1/3, and T is, 100 minutes. So I'm going to end up with natural log 1/3 over 100 minutes. So I go 1 divided by 3, take the natural log of that, divide that by 100 minutes. Don't forget this minus sign here. And I end up with K is a positive, K is always going to be positive, 0.0110. And what kind of units? Minutes to the minus 1. And there I got the value of K for that. I could ask you to solve, if I gave you K, I could ask you to solve for time. Okay, that sort of deal. All right, let's try another variation of this, and then we'll kind of close this out. Again, I cannot do every variation that is possible. I can teach you the principles. And I'm actually kind of philosophically opposed to doing every variation that's possible, because then the student doesn't have to learn how to do it. They just have to remember how I did it. And that's not what any professor wants, right? They want you to learn how to do it from the principles, not just memorize how the professor did it and have it in their notes. Okay, so I wouldn't do every variation for you anyway, even if you asked, because I want you to learn how to do it. Like I said, not just have every variation written down in your notes and then look it up and just follow how to do it. Right? I want you to have solved all the problems. Okay? So here, let's say, if the concentration of A is equal to 0.25 molarity, again, taking this reaction, A goes to P, and it is a first order reaction. if the concentration of A is equal to 0.25 molarity after, let's say, 375 seconds, where K, the rate constant, is 0. Let's say 310 minutes to the minus 1, what was the original concentration of A? So what am I always tend to slope up in my writing. I'm sorry about that. So here, what am I solving for? First off, this is not a ratio problem, right? So it must be, it's a first order problem, and they're having me solve for a number, so I use one of these two forms. Second, it's not a ratio problem, right, where I would do something like this, a ratio or a percent. It's one of these. And here I'm solving for the original concentration of A. So this must be AT, and they gave me K, the rate constant, so they want me to, and they gave me the time, so I'm able to solve for A naught. So if I rearrange the algebra, I'm going to end up with A naught is equal to AT divided by E to the minus KT. A at time T is 0.250 molarity. Then I'm going to have E to the minus, and what was K? 0.310 minutes to the minus 1. T was, I messed up. Here I have seconds. Here I've got minutes. If you have something like that, you would want to turn these seconds into minutes. But here I messed up, guys. I'm going to make this minutes. Okay? So I'm going to go 375 minutes. So 0.310 times 375, that's going to give me 0.250 molarity, E to the minus 116. And notice the minutes cancel out. Okay, and let's go here. That'll be the same as. Excuse me. I want to make it less complicated in my calculator. It's E to the minus. That'll be the same as 0.250 molarity, E to the positive 116. Right? If I bring it up, that minus becomes positive. 0.250 times 116, second function, E to the x. Ooh, it's going to be a big number. I hope I did that right. Right? And so I get this ginormous number, 5.97 times 10 to the 49 molarity, which is not a possible number, but I just made the number up on the fly. Let me see something here. 375 times 0.310, that does give me 116. Okay, so this is an impossible number. It's not realistic. There's no way you have a concentration of anything that is times 10 to the 49 molarity anything. Okay, that's not possible. But that's just a byproduct of I made the problem up on the fly. The numbers work, the math work. This is not realistic, okay? So it is the right answer. It's mathematically right, but not realistic in the real world. And again, I'll have to double check my math, but it's not realistic in the real world because there's no way you get anything that's times 10 to the 49 molarity. Okay, it's 49 moles of something in a liter of water. Not going to happen. I think that's just a product of I made up a problem going on the way, and the math so that the math works. But I didn't check it for realistic. But if you got this number, you know how to do it. Okay, it's just I screwed up in choosing, you know, numbers that make an unrealistic problem. But anyway, we'll go back over maybe some more of these for 0th order and 2nd order. But make sure you know how to do this. And notice I did have here, this is mathematically right, but it's not realistic. It's just I made up a problem on the fly. Okay then? All right, I'll talk to you guys next time.